In 2021, a team at Anthropic asked a bold question. Could we reverse engineer a transformer the way you'd reverse engineer a compiled program, turning its billions of weights back into human understandable algorithms? Their paper, A Mathematical Framework for Transformer Circuits, is the foundation that modern interpretability is built on. To make the math tractable, they studied a stripped-down model, attention-only transformers with 0, 1, and 2 layers, no MLPs at all. Start simple, fully understand it, and only then add complexity. Here is the whole architecture. Tokens are embedded into vectors, attention heads and MLP layers read and write, and an unembedding turns the final vector into output logits. The trick is how you look at it. The central object in the whole framework is the residual stream. Don't think of layers as a pipeline that transforms data step by step. Instead, think of one shared communication channel running through the network. Every attention head and every layer reads from this stream with a linear projection, does its computation, and then writes its result back by adding a linear projection in. Because every operation is linear, you can multiply the weights through the stream. When you do, hidden connections appear, what the authors call virtual weights, directly linking any pair of layers. A layer in the middle can send a message to a layer near the end without any layer in between even noticing. The residual stream is the shared memory they all talk through. How can so many layers share one channel without stepping on each other? Because the residual stream is high-dimensional, it can be split into many independent subspaces. Picture the stream as a wide bundle of wires. 2 layers only interact if one writes into a subspace that the other reads from. If they use disjoint subspaces, they simply don't talk. A layer can even delete information by reading a direction and writing its negative back, canceling it out. This subspace picture is what lets us isolate individual circuits. Instead of one tangled computation, we get many small, separable conversations happening in parallel inside the same stream. Now the key insight, the heart of the paper. An attention head looks like it has 4 weight matrices: query, key, value, and output. But for understanding, they always group into just 2 circuits. The first is the QK circuit, query times key, which decides where the head attends, which destination token reads from which source token. The second is the OV circuit, output times value, which decides the effect of attending, how the attended to token changes the output. Where to look, and what to do once you look there. These 2 circuits are completely independent, and you can analyze each on its own. There's a deeper reason this grouping is natural. Query and key only appear together as the product WQ transpose times WK, and output and value only as WO times WV. The model never used them apart. So the true parameters of a head aren't 4 matrices, they're these 2 low-rank circuits. That single decomposition is what turns attention from a black box into something readable. Apply this to the simplest interesting case, a 1-layer attention-only transformer. Because everything is linear, the entire model collapses into one clean product. Reading it right to left, the tokens, let each attention head move information with its attention pattern A and its OV circuit, then unembed to logits. The attention pattern itself comes from a softmax over tokens multiplied through the QK circuit. The beautiful part is that this isn't an approximation, it's exactly equal to the model. We've rewritten a neural network as a transparent mathematical expression, and now we can actually read what it computes. Expanding that product splits the model into 2 kinds of terms. First, the direct path. Tokens go straight from embedding to unembedding, with no attention at all. This term just captures bigram statistics, how likely one token is to follow another. Second, 1 term per attention head. Each says, the attention pattern A decides which earlier tokens get attended to, and the OV circuit, WUWOVOVE, decides how attending to a token shifts the logits. So the model is the boring bigram baseline, plus a clean, additive correction from each head. Every head's contribution is separate and interpretable on its own. So what do these heads actually do? They implement what the authors call Skip-Trigrams. Skip-Trigram is a pattern of the form. Token A appears somewhere earlier, the current token is B, so predict C A ... B, then C. Look at the real examples. A head sees the word perfect earlier, the current token is R, and it boosts perfect again, capturing perfect, or perfect. Another does keep, in, then mind. These are genuine in-context rules the head learned, copying and completing patterns it has seen earlier in the very same prompt. From raw weights, we recovered a readable algorithm. Here's a wonderful piece of evidence that this picture is correct. Because the QK and OV circuits are separate, a one-layer head can't fully bind which source goes with which output. It picks where to attend and what to predict, somewhat independently. That produces a very specific, predictable bug. A head that correctly learns keep in mind and keep at bay will also wrongly allow keep in bay and keep at mind, mixing and matching the destinations and outputs. The framework doesn't just describe the behavior, it predicts the model's mistakes. When your theory predicts the exact bugs you then observe, you know you're genuinely reading the mechanism. Many heads do something simple and important: they copy. If a head attends to a token, it makes that same token more likely next. How can we detect copying mathematically across thousands of tokens at once with Eigenvalues? Look at the OV circuit as a map from tokens to tokens and compute its Eigenvalues. A copying head maps inputs back to themselves, so its Eigenvalues are positive. Plotting the fraction of positive Eigenvalues per head, most of the mass piles up near 1. The signature of widespread copying. It's a compact, quantitative fingerprint of a behavior, read straight off the weights without running the model on a single example. Now add a second layer, and something genuinely new appears: composition. In a one-layer model, heads act in isolation. With 2 layers, a head in the second layer can read what a head in the first layer wrote. The authors identify 3 kinds. Q composition. The first head shapes the second head's queries. K composition. It shapes the second head's keys. And V composition. It shapes the values being moved. The distinction matters. V composition moves information around, while Q and K composition change the attention pattern itself, letting a later head attend based on what an earlier head computed. Through these, 2 simple heads chain together to compute something neither could do alone. Composition is the doorway from memorized statistics to real, multi-step, in-context algorithms. The most famous result in the paper is the induction head, and it only exists with 2 layers, built by composition. An induction head implements a powerful in-context rule. If the pattern AB appeared earlier, and you now see A again predict B, in plain terms, it finds the previous place the current token occurred and copies whatever came next. Watch it on real text. Having seen Mr. Dursley once, when the model later hits Mr. D, the head predicts Ursley. Having seen the Potters, it later completes Pot with Ters. This is genuine in-context learning, the engine behind a model picking up patterns from your prompt on the fly. How does it pull this off? It's a 2-head circuit. A first-layer head, called a previous token head, writes into each position information about the token that came just before it. Then the second-layer head uses K-composition. Its key is built from that previous token information. So when the current token, say the second Dursley, forms its query, it matches the key at the position right after the earlier Dursley. The attention pattern in red moves information from there. The OV circuit, the logit effect in purple, copies that next token forward. Where to look is set by composition between the 2 heads. What to copy is the OV circuit. 2 heads, 1 elegant algorithm. There's one more beautiful idea: path expansion. When you multiply out a 2-layer model, you get terms of increasing order. Order 0 is the direct path, the bigram baseline. Order 1 is each individual attention head. And order 2 gives virtual attention heads, pairs of real heads composed together, which is exactly where induction heads live. The authors even measure how much each order reduces the loss. The direct path and individual heads do most of the work, while the composed, order 2 terms are small on average, but they're precisely the terms that implement induction. Rare, but disproportionately important. Expanding the paths makes the whole computation legible. So what did this framework give us? A vocabulary for reading the inside of a transformer. The residual stream as a shared channel. Every head has a QK circuit that chooses where to attend, and an OV circuit that chooses the effect. composition and virtual heads that chain simple parts into real algorithms, and induction heads, the first concrete mechanism of in-context learning ever pinned down. Attention-only models were just the starting point, and the authors are clear that MLP layers and deeper networks bring real complications. But the concepts generalize, and almost every interpretability results since monosemantic features superposition. The discovery of induction heads driving in-context learning builds directly on this language. This was Anthropic's mathematical framework for transformer circuits, the moment the black box started to become readable.